protocol, right? So did you all gone through that? I have shared the recorded session and also shared the PPT and the interview. Aditi,
Yes, ma'am. You are audible.
Yes, yes, yes,
Yes,
baud rate generator. Have you tried finite state mission? So let me ask a few questions. So, how does your protocol handle the asynchronous communication without a signal, clock signal? Without clock signal, how the asynchronous communication will be handled?
based on baud rate generation.
Based on baud rate generation, okay. And can you explain the frame format of your protocol?
It starts with the start bit and has a 7-bit data, a parity bit to check whether the transmitted data is same as the received data, and it ends with the stop bit. The start and the stop bit will indicate the start and stop of the transmission of bits.
Okay, good. So coming to the parity, first of all, we have start bit and the data transmission of 8-bit and then parity bit and then stop bit, right? Parity bit is used to check the errors. Okay. So is there any other way like UART can detect the errors and what are the different types of errors present in the UART protocol? What are the different types of errors in UART other than parity?
framing error is there. Framing error.
What?
Framing error.
Framing error. Okay. What is mean by framing error?
Like stop and stop bit is not detected that time.
Okay. And next, there is a parity error. Parity error means we will just check with the odd or even number of ones or odd number of ones. Framing error, just whenever the stop bit and start bit not detected, then we get the framing error. And whenever the receiver, we use lot of FIFOs and buffers here, right? So whenever the buffer is full or FIFO is full, the new data arrives before it data read, we'll get the error. So in that case, we'll get overflow error or overrun error. And we also have the break condition. Break condition in the sense, suppose there will be two lines here, transmitter line, receiver line, and both are bidirectional, and also full duplex communication. In UART, we have full duplex communication and also half duplex communication. Okay, so whenever the receiver line is low and for full like long data format, data frame or data transmission, whenever the receiver signal is low, there we will get the break condition. That means suppose 32-bit data is there. For 32-bit data, the receiver line will be low for the longer data formation. Okay, in that case, we'll have the break condition. That is a different types of arrays we face in a UART protocol. Mostly top two errors like parity error and the framing error are most important. We can check even parity error, we can write in the program. And coming to the baud rate generator, before baud rate generator, I think everyone understood the UART communication. Suppose in a system on chip, how the communication will be happen between high speed blocks like processor or memory, or whenever we connect with the outside devices to the laptop or to the mobile phone, external connection. So where we use different types of protocols like peripheral protocols or bus protocols, serial communication protocols. We use uh, different cases, right? We need to consider the high speed, low speed, okay, serial communication, parallel communication, intra, inter. So there are different classification. So this is the top level block diagram we are going to discuss today, and I will show you the um, how to install the tool today. Okay, installation process, QuestaSim. For UVM, we are using the QuestaSim. For system Verilog also we use QuestaSim, right? Today I will explain. If time is not there, tomorrow we'll explain. Okay. So today we are going to design this top level block diagram where we get the baud rate generator, transmitter, and receiver. And also we discuss the how we can design the transmitter and receiver, right? So transmitter have different types of blocks like FSM, piezo, parity generator, and mux. Can you explain this the functionality of transmitter? Anyone? Hello. Fast. Manoj Kumar, can you explain? Or Kalyan? No? Okay. See, did you forgot or what? Roshini, can you explain?
Yeah, it's I'll try. Maybe I will miss some points. Okay, so the transmit. So the first stage in the UART transmitter is the transmitter FSM. So when the start bit is recognized, it will go for the baud rate generator, and after 16 cycles, it will it will receive that data bit, and there is a counter that will count until 8 bits is received. Once the 8 bits are received, it will check for the parity bit, and then it stops the data. So that is the working of the finite state machine. And then I'm not sure about the piezo one. And then there is a mux that basically selects between the start bit, the data bit, parity bit. The parity bit will be generated from the parity generator and the stop bit. So depending upon the select signal, any one of the input is selected in the mux and is given to the data out.
Okay. So what about piezo? Like parallel in serial out? I already told, right? So in a system, in system on chip, there will be multiple number of blocks, right? Suppose here processor and memory is there. Processor to memory to some subsystem. It will do the parallel communication, and here UART is a port, right? It's a port where we connect some external device. So here within the processor, within the system on chip, overall data transmission or receiving can be done in a parallel processing. Overall handshake happened between transmitter and receiver in parallel. Okay, but here whatever we are transmitting this data to some external device connecting through the UART port or some channel, wired channel, it should follow the here your protocol is a serial communication, right? So here whatever getting the data from before master or slave, it will be parallel data. So this parallel data we need to convert to the serial, because your protocol or USB can accept only serial communication. Okay, so that's why here we are converting the data in a parallel. Here is the transmitter side. This transmission 8-bit data is nothing but which is coming from the other slave. So here there is a master. Suppose APB protocol is there, APB master and APB slave. Here APB protocol means it can do the transmission parallelly. Okay, from transmitter to receiver, it do parallel communication, and whatever here it is receiving the data, it will be also parallel. Okay, slave also parallel. If any master is connected here, if APB master is connected here, then this parallel data is directly communicated to the master. But here we are connecting your transmitter, your master. So your master accept only the serial data. That's why whatever the parallel data is coming here, we will convert to the serial. So that's why here we are using PISO. So the serial data is converted one by one bit, converting to the serial and sending to the data bit in a frame format. Okay, so this mux is nothing but in frame format we have four different conditions, right? One is start bit, data bit, parity bit, stop bit. So through this multiplexer selection line, we are controlling start, data bit, parity bit and stop bit based on the selection line. Okay, and also here there is a parity bit. Parity bit, how it is generating based on the parity generator, and also input, whatever the input is coming here, the same input will be connected to here. Okay, so if input is transmitted and at receiver side it should receive the proper data, correct data. If correct data is not received through the parity generator, we can check only odd number of ones and even number of ones. So that can be done through the parity generator. Okay, so this is what your transmitter. Today we are going to design your in a Verilog. Okay, overall RTL design as per the curriculum. YORT is in a Verilog, I2C and APB are in system Verilog, APB, AXI and AHB are in UVM. Okay, today we will discuss YORT in Verilog HDL and also test bench in Verilog. But still, if you want UVM verification for YORT, I can share. Okay, so this is what the transmitter side block diagram. We need to design every block properly, and then this is what the final state mission. So whatever the block is there here, FSM. So here is the final state mission. First of all, every final state mission will be started with the ideal state and go to stop bit and data bit and then parity and then stop. I already explained all these things in the last session clearly. Okay, if anyone forgot, just prefer that session. Once again, go through that session. Okay, and coming to the receiver. So from transmitter side, we transmitted the serial data properly. Now receiver need to get the data. Okay, so one by one bit 1, bit 2, bit 3, like that serially one by one bit it is getting. It will be detect the start bit. Whenever the start bit is stopped, so it's sending the data one by one to the receiver. So here it should convert that serial data to parallel output. Why? The transmitter to receiver is a serial communication. Now this receiver is a slave and the transmitter is a master. So this slave will be connected to another master. This master may be any master. Maybe here again this master may connect with the slave, which is a APB protocol. Again this slave will be connected to the another master. Here this master may be the processor. Processor means high speed. Here it use the AHB or AXI communication. But this APB data, how it will be converted to the AXI, middle we use the bridge interconnect. Okay, so this is what the connection between parallel communication and serial communication, right? So that's why here serial in a parallel out. So whatever the data is receiving here serially, that is converted to the parallel to give the input to the APB or whatever the parallel communication protocol. Okay, so serial in parallel and parity checker. In the receiver only we will check the parity, right? If parity load is high, we'll check the error based on the even parity or odd parity. And then stop bit checker. Whenever the stop bit is high, we can stop the receiving the transmission. Okay, next FSM. FSM also discussed. There will be 4 states: ideal state, data, parity bit, and stop bit. 4 states. If any parity error is generating, then the parity error is given to the ideal state. Okay, I think everyone understood the transmitter side and receiver side block diagram. So now, how transmitter and receiver are connected each other, how the synchronization happened between the transmitter and receiver. Okay, so what technique we are using in the UART protocol? What technique we are using in the UART protocol? Nothing but baud rate generator, right? What is mean by baud rate generator? What is mean by baud rate generator?
It actually generates some clock signals, like to control the transmission and the receiving part. Some clock signals has been this will be generated by the generator.
Okay. Any other answers?
It is how many bits we can transfer per second. So it basically defines the communication speed.
Okay. Okay. So baud rate generator is nothing but in the asynchronous, we don't use the clock, right? So it just defines the number of bits per second, BPS. We call it a BPS. So it whatever the channel is there, over the channel, it do the transmission serially one by one, bit by bit. For example, we have different baud rates. Where I have given the baud rates here. 110 baud rate, 300, 1200, 2400, 4800, 9600, 19200. These all are fixed baud rates. Okay, that means 9600 means what? 9600 bits per second or transmitted. Okay, so transmitter side we need to take a fixed baud rate, and receiver side we need to take fixed baud rate. If transmitter side you are taking 9600 and here receiver side you are considering 9600, so transmitter side it 9600 bits per second or transmitted, receiver side also it receive at the same level, both baud rates must be same. Okay, so mainly this is for asynchronous protocol because there is no shared common clock. Okay, but how we can generate the baud rate in terms of coding, and what is the formula? Last session we discussed for baud rate formula.
Clock frequency divided by the baud rate divider.
Okay, baud rate is equal to clock
Yeah,
frequency by division
baud rate
into
baud rate.
16.
Yeah.
16 means what is this 16? Sampling rate, right? So here if you observe the calculations of baud rate in UART determines the speed of the data transmission measured in bits per second. So baud rate is equal to clock frequency and baud rate division. So how to calculate the baud rate system clock frequency Suppose if the frequency is 16 megahertz or 20 megahertz, it is fixed. And divisor also fixed. I already told, right? The transmitter side and receiver side, if you transmit 8 bits, 16 will be the fixed. And your maximum size is 8. And then in a further versions, we have 16-bit and 32-bit also. But in 16-bit, 32-bit also, we need to divide into the number of transfers. Okay, in first transfer 8 bits and then in second transfer 8 bits. Like that, we need to divide into the transfers. So that's why baud rate is fixed with the 16. Okay, so suppose here we are using the formula and we are getting the baud rate. Okay, so here 16 megahertz by 16 is equal to some 10 lakhs bps, bits per second. Okay, so like this we can calculate the baud rate. But I have a question. Suppose if transmitter side it is working at a some baud rate and receiver side it is working at a different baud rate. Okay, then what happens?
Frame error.
Yeah, frame error. With
Suppose your at transmitter side it is working at 9600 baud rate and here it is working at 115200 baud rate. Okay, so will the baud fails, then what is the issues we can face and how can we overcome this?
By changing the clock frequency at the receiver side.
Okay, clock frequency at receiver side, but in which cases we will get like this? Because if you take from our side, we never take like this. We will consider same baud rates only. But maybe sometimes if baud rate is less for transmitter and baud rate is more for receiver, so like in baud rate mismatch cases, what are the different methods we can see use? Can we adjust the divider, clock divider?
Yes.
How can we adjust the divider? Frequency is the same and baud rates are different, but how can we match both the baud rates? What is the example? What is the formula for divider?
Sampling rate.
Divisor is equal to clock rate, clock frequency by 16 into baud rate.
Okay.
So here, whenever we change the divisor value, so baud rate will be changed, right? So
Yes.
how much, according to this, how much a divisor value we can change for 9600 to 11250, 5200? Suppose if 9600 means what? CPU have more time to process each byte. At 115200, baud may not process data fast. It may be lead to the buffer overruns. So what is the solution for that?
we can have some kind of mechanism which will automatically detect this baud rate problem and it will change the values according to that.
Okay. Shall we use any controllers, memory controllers or P4 memories?
Yes,
some
yes.
buffer memory will be.
Buffer memory we can use and we can make it same synchronization, right?
Yes, yes.
Suppose if some microcontrollers are connecting with the 16x baud rate, 16 baud rate, or 88x, so oversampling. Sometimes you do oversampling for your reception. Microcontrollers or 16 or 8 or 32, but for UART it is oversampling whenever we are connecting. Okay, so in that case, how can we do that whenever there is improper sampling rate?
So whether it will be similar to a CDC kind of scenario where you have one side one clock frequency, another side another clock frequency. Is it similar to that?
Okay, so both clock frequencies can be used. Huh?
Ah, yes.
Or
But here
controllers
also the
can be
mismatch is with respect to the baud rate, correct?
Hmm.
So
Okay.
if we, in the receiver side,
Hmm.
we can use a buffer kind of a thing. So from the buffer reading side, that from the reading side, if you fix the baud rate or some, if you use some control mechanism to get the data with the same baud rate, then that will be good because if we have some data storing element at the receiver side.
Okay. Okay. Fine. Suppose you need to send larger files over UART. So how can we ensure that reliability transmission?
If larger data is there in the sense,
Maybe you can use CRC 1632.
then we have to depend upon that transmitter side stop and start bit, and then we have to store the data accordingly at certain, because there is no, if that much FIFO size is limited, so if large number of data is there, like we will require a large memory. I think that won't be a solution for UART side because
That
it's a
the parity will not be worked, right? So in that case, what you will do without using the parity? Parity concept is there in UART. Other than parity, we don't have any other concept. So without changing the actual functionality, how can you detect in terms of 30 CRC 16 or 32?
means we have to look into the bits, means what the data which what it is coming, or the like from the baud rate, or from the baud rate we have to how to count the number of cycles. Some controller mechanism will be required. That's what I'm thinking.
Okay, maybe like acknowledgement or
Ah,
not acknowledgement.
yes.
Okay. Okay. Um, So these types of questions may be mostly getting from the interview. If you go with some experience level, okay. If you are fresher, just you need to know about how to calculate the baud rate, how to calculate the divisor, transmitter, receiver, frame format, block diagrams are enough. But if you go to some experience level, you will get these type of application oriented questions like suppose there is an embedded device. Mostly we use UART with embedded applications, right? Embedded device need to wake up from sleep mode. Okay, so when receiver UART receives the data, so how can you implement that sleep mode condition with UART? Like you need to implement multiple device your communication, so how can you manage the bus? In your protocol we have only single bus 8-bit data we can transfer to that, so you need to implement a multi-device your communication, so how can we manage that? What are the possible approaches? And also how can you optimize the UART for high speed data transfer like 1 Mbps? Here we are just sending in a BPS only, 9600 BPS or 4800 BPS or even 115200 BPS, just in BPS. But if you want to transfer in terms of 1 Mbps, so what are the UART strategies we can use? Do we need to use any controllers or FIFO memories, or can we reduce the interrupt frequency? And also we can make the efficient framing in terms of 8-bit. We can take multiple transactions using the same frame format, and also RTS CTS signals are there, right, in UART protocol. We can use those signals for flow control.
What is mean by RTS? I didn't get my.
RTS and CTS we already discussed here, if you remember, for interrupt handling, and here for flow control. It
Okay.
works request to send and clear to send.
Okay.
Okay, so now we will discuss on the programming, how to design the UART protocol, overall structure, whatever the transmitter receiver block diagrams are there here, same thing we are going to put in terms of RTL design. So everyone clear till here? Any doubts?
No, I didn't get the solution for that question you have asked, right? So if you have to baud rate at different baud rate at the TX side and RX side, how we will resolve that one?
How you will do between baud rate here to there, right? We can use the frequency buffers. You can use here by using the divisor value. Whatever the divisor value is there, if you increase or decrease the baud rate, both you can match, right? Here you are not changing the baud rate. Baud rate is 9600 fixed, and here 115200 fixed. Baud rate you are not changing, but still you want to match between these two, then you can change the divisor value. Divisor just sampling rate increasing. Here clock frequency is also fixed. Clock frequency is taken at transmitter receiver side, that is fixed. So in that case we need to change the divisor value, or else we can put the frequencies or controllers like that.
Okay. Thank you.
Girls, any doubts? Shweta and Roshini, Vinita.
Sorry, I just joined now. It's 5 o'clock for me. Okay.
So here the frequency you are dividing, right? That frequency is nothing but like you mean APB or something, which will drive the UART.
Frequency, if you talk
This
individually,
clock.
we will consider based on this UART protocol. But if you are connecting from the APB to UART, then mostly APB frequency will be sent to here. Whatever the master slave is connecting with the UART, same frequencies it will be worked. There will be some frequency mismatches will be there. APB means it will connect mostly with the high speed, but nowadays UART never connect with the APB. We use USB, so frequency matching will be there between those protocol to USB.
Okay. So who is driving that will be the frequency comes into the formula. It will be anything, right?
This UART protocol which is driving.
Yeah. So in the case of APB, if it is
No
driving,
frequency, APB slave frequency will be connected to here, master to slave. Same frequency, but little difference.
okay. So that frequency only in the formula we are putting, right?
Yes.
Okay. So another thing is like the previous mouses we are connecting, right, with the UART cable, like that UART. So that round one. So here the TX is the mouse, right? The transmitter. UART transmitter is mouse, correct?
Here?
I mean, let's consider mouse is connected to our
Okay.
PC. So TX is mouse, right? Transmitter.
Okay. TX is not a mouse.
Okay.
Our port, whatever we are connecting the port here in laptop, that will be the transmitter. Mouse will be the receiver.
Mouse will be the receiver.
Port will be the transmitter. We are just connecting the plug. Plug is not a transmitter. Plug is a receiver. Port will be the transmitter.
Okay, but the moment whatever we are doing from the mouse, that only to be go right to the receiver. Then only receiver will proceed on that and give the.
Whatever we are doing with the mouse, that will be coming to the this computer only. But the computer signal also important to mouse. Without giving the computer signal, mouse cannot work, right? So if mouse having that UART port, that will be the transmitter. But mouse doesn't have the port, UART port. Only for the computer having the UART port, and it just having the cable connection where we connect the port, the pin. That's it. But actual port implementation will be in the wherever we have the port connection.
Okay, so I mean CPU only
Suppose
with the
if you connect the printer also having the UART or USB port to port connection. So it will be working as a transmitter and receiver, both bidirectional. Transmitter and receiver or interchange. Okay.
Okay.
But here from mouse point of view, it will be another type of port. Suppose if you connect the mobile phone having some other type of port, C port or B type port pin like that. But laptop having the USB or UART. Okay, so actual implementation will be having here with USB in laptop. Mobile phone having its own B type or C type, whatever the hardware is there, according to that, it will be having that hardware implementation. Okay. So the transmission between these two happen through these rules and whatever the frame formats we are using from USB to C port. Same as a mic system also. If you connect any earphones, actual UART implementation will be in laptop only, because from here only we are sending the signal.
Okay, and the start bit, stop bit you're talking.
Is
So every time who will add these things and send the packet?
that will be coming from the internal system processor instructions. Through the processor instructions, it will be sending the data signals, right? So whatever, wait, let me show. If we talk in hardware point of view, there will be a UART protocol here and connected a printer or just a music system, earphones. So this earphone is connected to UART. Whenever external device is connected here, immediately we will get the pop-up message. Okay, so that means immediately it will be connected to the processor. In terms of hardware, it will be connected to the processor. Processor will get the instruction. Okay, some external device is connected to this laptop or computer. So based on this instruction, what type of data it is going to get from the processor, what expecting. Maybe it may be some mobile phone or any device. The processor doesn't know which device is connected, right? Based on the instruction. So based on what expectations from this, the communication will be happen. So based on that instruction, internal data handling can be done. It will be sending the particular data, and that data will be communicated to here. That can be done overall between these processor to internal components to UART. The data coming from packets to UART. And here the start bit condition. Suppose here 32-bit APB protocol is there. APB protocol is working with the 32-bit data. That 32-bit data need to send to UART protocol here. But this UART may be not working with the 32-bit. Okay. But this 32-bit data, it will put in a FIFO buffer first, because we know the transmission frequency is not match between APB and UART. Okay, if not match, if we don't put, if we directly connect, we have the data loss, right? So that's why we use the FIFO buffers. Or if you go beyond, suppose some memory is connecting to the UART protocol, then controllers will be connected between data transmission. Controller means So at what time the frequency matches will be done here. Okay, so now UART will receive 8-bit data faster. In this FIFO buffer, 32-bit data will be stored temporarily. Based on the transfer, here we are initiating the transfer. So first 8-bit will be transferred based on start bit and stop bit. Once that 8-bit transfer is completed, again it will initiate 32-bit and then again it will, 8-bit and again 8-bit, like in 4 transfers it will be done, whole 32-bit data process. Okay.
Okay. And
Here
this socket, this socket which you're talking, our main IP will stand near to the CPU, right? Not in the socket. The socket is just a connector, right? Or
yes,
there only IP will stand.
yes, it is just a connector. Actual hardware will be connected into the near overall CPU level. Socket wise, we'll just connect some wire connection to the socket.
Yeah, inside the socket that will be connected to the UART IP.
Yes.
Right. Okay. And here the baud rate divisor you are telling 16. That that will be the fixed on what basis?
Fixed. Based on
That because of 8
how much data we are transmitting. 8-bit data means transmitter side 8-bit, receiver side
receiver side
8-bit,
8. Okay.
16 total. That is fixed mostly.
Okay, so in the latest version, you are talking like the data has increased, right? Data size. So
In that case, the
just
baud rate also will be increased. Just sampling data. At what data rate we are doing the sampling. So based on the data, whatever we are transferring, based on the sampling rate will be changed.
but the same concept. I mean, that 32-bit you are talking that only, is it? Storing in the FIFO and then will
In
8
latest
only.
versions, in latest versions we can send the 32-bit directly, but in this if we talk, we divide 8 bits only because you are having 8-bit only. Even if you go to latest version also same 8-bit data only we can transfer in one single transfer, one single frame. That 32-bit will be divided into the 4 transfers. Okay.
Okay.
So whatever you are telling more data, in the sense in UART we don't have that version. In USB, the most popular protocol which is replaced with UART is USB. So there we use 32-bit data, 64, even 128-bit also.
So in latest version also, however the data will come, it will go split and 8 and then only will transfer. Only the frequency of transmission we are increasing the speed.
Frequency, transmitter and also receiver.
Yeah, I mean the baud rate we will increase or something like that too.
Yes, but in UART only we have the baud rate concept. In remaining all protocols, we don't have any baud rate concept.
Yeah,
All
there
are
will
the
clock.
clock channels only. Yes.
Okay, so maximum frequency which what UART will, I mean baud rate will support here. UART.
Maximum frequency in it doesn't support in megahertz. I think it's 200 hertz only.
Okay, so beyond that we have to go. That's then we comes to the USB.
Yes.
Okay. Yeah.
So
Yeah.
16
Hi.
megahertz. Yeah, tell.
When we require large amount of memory, or it is coming from APB or some different interface, then we require a memory along with a memory controller, correct? At the transmitter side, just before that FSM you mentioned.
Memory controller between before the FSM here.
Yes.
Mostly memory controllers are connected to the processors and memory. Okay, and also connected to these. You can connect a high speed FIFO or high storage FIFO, or else any controller also fine.
Means
Now,
my query is like if the data is coming, some chunk of data, some bulky data, the framing will happen in the with respect, the controller will be doing the framing, or the FSM will be doing the
no.
framing.
Controller will not do the framing. Controller part, its functionality is different. Just it will be helping to transmit the data properly between memory and the uart. And whatever the framing, in the sense you're talking about the transmitter of this 8-bit data, right, through the frame
Yes,
format. So
yes.
that will be totally hardware part of uart. Let me explain the program. You will get the idea.
Okay.
Others, any doubts? So suppose here is the uart. First, we will start with the transmitter. Okay. So what are the different blocks are there in transmitter? First one is a FSM, piezo, parity generator, and a multiplexer. So multiplexer, parity generator, piezo, and FSM. This is top level UART transmitter. Okay. So in top level UART transmitter, what it is connected? First of all, UART TX. What are the signals out there? Clock, resetter, TX starter, TX data, and TX data out busy, TX starter, TX data, and TX busy, TX data out, and clock common, baud rate clock, reset also common. Okay, and input clock, input reset. This is not direct clock. We will generate through baud rate. Okay. Next, input start data in outputs or declared, and some temporary variables like parity, out, piezo, op, and multiplexer selection line, load signal, shift, parity load. Now, here connecting the DUT of 4. We need to design the 4 individual blocks, right? One is for mux. So mux input and outputs are given here. So whatever the mux input and output, start bit, data bit, stop bit, parity bit, data out, and select. So next, parity. What are the inputs and outputs, and parallel in serial out, and final state mission. Okay. Now we will design individually. First, we'll start with the mux. So how can we write the multiplexer program? Module TX mux selector data bit parity bit and TX out. Whatever the signals are there here, same signals. And then declaring input output signals here, and always at the rate of its multiplexer is a combinational, so we can put all the inputs here, or simply start select 2-bit binary. 00 means, what is the 00 case here? Start bit. 01 means data. 10 means parity. 11 means stop bit. So 0 means start. Whenever the start bit is 0, then transaction is initiated. And 01 means data bit. Data will be transmitted. 10 means parity bit. 11 means 1 stop bit. Okay. So whenever the stop bit is high, it will stop the transferring data. Okay. Next, parity. You already know parity can be checked in even or odd. And in terms of gate, if we talk, we have a XOR gate to detect the parity. Okay, so we use XOR operation or else XNOR operation. So module TX parity, clock, reset, all the inputs we need to mention here, and input and output declaration always at the rate of posage clock and negative posage reset. So always at the rate of pause, clock and reset. If reset is high, parity will be 0. Else, if parity load is high, load is a control signal. So in here, if you see load data is a control signal. And if load is high, parity out is equal to XOR of parity in. So what is the XOR operation? Is it odd parity detection or even parity detection?
Even parity?
So whenever there are odd number of ones in the input, output will be 1. So whenever odd number of ones in the input, output will be 1. So it detects the odd parity and even parity corrector. Okay. So parity out, XOR operation of data input. So for every what is this operation? Can you tell me, is it logical operation or bitwise operation or reduction operator?
Reduction operator.
Reduction operator. So XOR of input. And then else parity out. How it will be done? Reduction operator. Suppose input having like this 2 ones. So what will be the output now? It should be 0. So 0 1 means what is the output? 1. 1 0 means 1. 1 1 means 0. 0 0 means 0. So final parity detect output will be 0. That 0 will be assigned to parity out here. Okay. Else parity out equal to parity out. This is how we can check the parity. And then next, parallel input, serial output. So whatever the data is getting here from other slave, in this master, it should convert the parallel data into the serial data. For PISO, we have lot of methods, right, to convert data parallel to serial. We designed using behavioral modeling, data flow modeling, gate level. There are a lot of methods. You can use any one easy implementation wherever we can write within a single bit. Simple logic, you can use that. Mostly we use behavioral only. So module, PISO, transmitter, clock, reset, load, shift, PISO in, PISO out. So input, clock, reset, load, shift, and parallel input 7 down to 0, 8-bit data. Parallel output, parallel in serial out means serial output, single bit data. And to store that parallel input, just 8-bit temporary variable we are using, and output is getting T of 0. That means 7 down to 0, right? 7 bit will be the P of the starting bit, 0 will be the last bit. So that's why T of 0 assigned to the last output. Always at the rate of pause, clock and reset begin. If reset is high, where temporary variable equal to 0, else begin. If load is high, parallel in serial out means what? First we need to load the data, parallel data, and then we need to shift the data. Okay. So whenever load is high, parallel data will be loaded into the temporary variable. Whenever shift is high, that parallel input will be shifted 1 by 1 bit to the temp. 0, 7 temp of 7 down to 1. Like that, it will be shifted to the temporary variable 1 by 1 bit. Can you explain anyone the logic? Did you understood the shift operation here?
Yes, ma'am.
This is a right shifting operation, ma'am.
What shifting?
Is this right? Is this right shifted?
How it will be shifted? Just tell. You need to tell that. 7 down to 0. 0th bit is a last one assigned to piece of outer. So is it right shifted or left shifted? And also temp 7 down to 0 is right shifted. So 1 bit right shifted. So 7 down to 0. 7 down to 0. This 0th bit is assigning to the main data outer. So remaining all bits will be shifted one by one. Whatever getting to last bit, that bit will be the data outer. And also if you see here, temp is equal to 0. 7 down to 1 is shifting right. 7 down to 1 is shifting right. And 8th bit, whatever it is there, assigning 0. Okay, so now it is it right shift or left shift?
Right shift.
Left shift.
Left shift. How?
So we are assigning the last bit to data out, and then you told we are shifting the other bits from 7 down to 1, and we are putting the last bit 1 tick be 0.
But here 7 down to 1 is shifted right. Actually, we should have 7 down to 0. But this 0 is going to here, and whatever this 1 is there, 1 shifted to here, 2 shifted to here, 3 shifted to here, like that 1 by 1 is shifted. Then how you can tell it's a left shift?
It will be right shift only, because from one D flip flop, the output of one D flip flop will go to the combinational logic and of some AND gate, and the second to the second AND gate, the input will be coming as a parallel ring.
Okay. Always
The
it should
last, so the last D flip flop will, the last D flip flop will give the output actually.
be.
So it will be right shift only.
Always it should be right shift only. Understand the point clearly. Temp is equal to 0 bit and 7 down to 1. If it is a left shift, are you transferring the data from transmitter to receiver or receiver to transmitter? Transmitter to receiver means the bit should be shifted left, right only. One bit, next one bit, and next one bit, and next one bit. Like that, one by one bit will be shifted. Whatever MSB is there, in MSB bits, it will be added zeros, and one bit will be shifted right towards right. It's a transmitter side, correct? If you write in a receiver, then serial input will be converted to the parallel. That logic is different, but parallel to serial means it should always shift serial data towards right only. Okay, here MSB bits it keep on adding 0, and LSB side keep on shifting the data one by one data. Okay,
I got it.
temp is equal to temp end. Okay, clear everyone? Piso block. Okay, next. Mux completed, parity completed, piso completed. Now FSM. How many of you don't know FSM, how to write the program? Everyone know? Okay. So first of all, how many states are there? 5 states. Ideal, start bit, data bit, parity bit, and stop bit. We need to declare all these 5 first. So module FSM, just check what are the inputs and what are the outputs. So TX start and count is a temporary variable. TX start, select, load, shift, parity load, TX busy. So input log, in out reset, and TX start, select signal, and load, shift, parity load, TX busy. And count signal. Count is to count number of bits where we transmit from transmitter to receiver or receiver to transmitter. Total 8 bits. It will be counting that 8 bit. And reg count enable, write data done. Whenever counting all 0 to 7 count is completed, so data is done. That means transmitted the data. Same here. If you see bit, data bit, whenever count is equal to 8, then still if it is not equal to 8, still it is in same loop. That means data is transmitting. Whenever count equal to 8, count operation is completed. That means it transmitted 8-bit data. So going to parity bit. Parameter, ideal, start, data, parity, stop. We need to declare all constant values. And also what is the present state, what is the next state. And assign data done is equal to, when the data will be done, whenever count is equal to 7. Always at the rate of posage clock reset. If reset is high, count equal to 0, else begin. If count enable is high, count equal to count plus 1. Counter logic, else count equal to 0. This logic is same for all FSM. Initially we need to write, and this also present state, next state. If reset is high, always the present state will be ideal. If reset is not high, present state will be next state, right? And always at the rate of case present state, ideal, we declare ideal, start, data, parity, stop. Here is the main functionality. And next always block control signals. Enable and disable the control signals. So here, if transmitter start is high, then what is the next state? If transmitter start is high, next state will be the start bit, or else ideal. Okay, same thing right here. If transmitter start is high, next state will be the start, else next state will be the ideal. And if start signal, present state in the start, so next state will be the data. Present state is in data. If data done, then next state will be the parity, else next state will be the data only. And next parity, next state equal to stop. Stop signal, stop is current state. If TX start, again TX start is initiated, then it will go to start, else it will go to ideal. So in which case it will be worked, if it is a 32-bit data, it will be waiting for second transfer. Again the loop will be repeated. But if it is only 8-bit data, there will be no second transfer. So it directly goes to the stop state, ideal state, if there is no transfer. Okay. And always at the rate of start, case present state. We are in present state, ideal. So if select ideal state, begin, select equal to 2-bit, binary 1 1, load equal to 0, shift equal to 0, parity load equal to 0, TX busy equal to 0. These all are control signals. Why select is 1 1 here? What is mean by 1 1? 0 0 0 1 1 0 1 1. 1 1 means stop. Okay. So in ideal case, it will be always stop. In start state, it will be 0 0 start. It detects the start. So here all signals are 0, and in start case, the select will be 0 0 because start condition, and load will be high. Here we need to load the data, right? In start state, we need to load the data, and shift will be 0, and parity load equal to high, because we need to check the parity, initiate the parity. just initiating the parity. We are not checking here. And TX busy. Here transmission will be in a busy state. Once we initiate the transfer till it completes till 8 number of bits, it will be in a busy state only. So TX busy is equal to 1, count enable equal to 0. Okay. Why? Count will be started in the data, not here. Here we won't start the count. Whenever we are initiating the transfer, for 1 by 1 bit, we enable the count. Okay. So now current state is data. So which signals we need to enable? These all are control signals. If you may get the doubt why we are using all those signals. If you see here multiplexer, all these signals dependent on selector. So this select signal we are giving in the FSM. Okay. And if you go to parity, here parity out is depending on the parity load and reset. This reset and parity we are assigning the value in FSM. Like that, if you go to PISO, here load is there, shift is there. All these signals will be dependent on FSM. Okay. Like that, your transmitter side and also remaining control signals all will be dependent on these FSM signals only. Okay. So current data, current state is data. So if selection line is equal to 0, 1, then only it will be transmitting the data. Okay. So load is equal to 0 because already we loaded the data in before state. So in current data state, just we need to shift the data. So shift enable is high. Whenever shift enable is high, then only in PISO the data will be shifted, right? Whenever load is high, the data will be loaded. So here shift is high. And parity load equal to 0, and TX is in busy state only because the 8 transfers, 8 number of bits it need to transfer. So it will be in busy state only. And count enable equal to 1. Whenever the count enable equal to high, then only it will do the count equal to count plus 1. Okay, so that's why here count enable equal to 1. So data state also completed. Now parity bit state. So coming to the parity, select equal to 1 0. 1 0 means parity. 0 0 means start. 1 1 1 0 0 1 means data. 1 0 means parity. 1 1 means stop. So here selection line equal to 1 0. Load equal to 0. Shift equal to 0 because we are not loading any data and shifting any data. Parity load, already we loaded the data into the parity. And TX busy equal to high. Count enable equal to 0. And coming to the stop. Here select equal to 1 1, load equal to 0, shift equal to 0, parity equal to 0, TX busy is high, count enable equal to 0. Based on these selection lines and based on this FSM, actual design is going to work based on the functionality. Clear? Any doubts in FSM? Simple FSM.
I have a doubt.
Yeah,
There are two cases for select line equals to 1 1, right? Stop a case and ideal case. So when the select line becomes 2 tick B 1 1, so there is ideal case also, stop case also. So how it will decide which one to do one, like which one to execute first?
Here we written the condition for ideal. If TX start is high, then only it will go to start, or else ideal. Ideal is also nothing but stop condition. Okay. Here in stop case, when TX start is high, we are in stop, but TX start is high, then it doesn't go to ideal. It will go to TX start, and again it will continue from start bit like this. 4 transfers for 32 bit. But if it is only 8 bits, it will go to ideal state and stop. Okay, that's why here stop is nothing but in ideal case also it will come 1 1 only because we don't have any data to transfer, right? That's why. And where you have seen here select signal equal to 1 1. Yes, ideal case, stop case. Okay,
So,
clear?
Directly the counter incrementing part.
Counter incrementing part we have written in the piso. Not piso, FSM only. Here, count enable is high, count equal to count plus 1. So
Okay.
whenever count is reaches to 7, data is done. Still till 7, it keep on running. Count equal to count plus 1.
So overall, this FSM is controlling the TX frame generation. Correct.
This TX. Not only FSM, all submodules.
Also.
Okay. So now we have designed this FSM and the TX block diagram. Okay. Now we need to design receiver block diagram and also receiver finite state mission. Okay. So coming to the receiver block diagram, what are the different blocks available here? Detect start, SIPO, parity checker, stop bit checker, and receiver FSM. All these 5 blocks we need to connect in the top level UART receiver. And then we need to design individual blocks. Okay. So go to UART receiver. So detect start, serial in parallel out, parity checker, stop bit checker, and ORX receiver. So module, receiver, all are connecting in the receiver, clock reset, data in, parity, data out, stop error, receiver done. So same, whatever the signals we have here, same signals you need to mention there. And just take the temporary variables. Assign receiving is done. When the receive is done, whenever the stop bit check. Okay, check stop. So whenever stop bit is high, for start 0, stop high. So whenever the stop bit is high, then receiving is done. So stop. Next, we are connecting detect start, serial in parallel out, parity checker, stop bit checker, receiver FSM in a top level here. Detect start, serial in parallel out, parity checker, and stop bit checker, receiver FSM. DUTs, all DUTs. Okay. Now we will design individually. First, detect start. So how we can write the code for detect start? How can we write the detect start? Just think, how can we write the program logic?
Means the first bit whether it is like edge detector means from the frame for whether the first bit equal to the start bit or not, we'll check and we can say the frame is starting.
Okay. Any other answers, others? How can you write the logic for detecting start bit?
So for this detect start, we are connecting this RS doc int into the RS data in like that we are writing.
Okay.
Can you show me the design once? Yeah, so here we are connecting this rx dot in with the this detector start. So we are connecting this with the first
Zero.
rx dot, yeah, zeroth with the rx dot in, like that. Uh,
Okay. If Rx in of 0 is equal
then,
to 0, then it is a starter.
yes.
Okay. See here. Module detect start, input will be Rx in, output will be start bit detected. Assign start bit detected is equal to not orin. That means orin equal to 0. Then start bit detected will get the value, 0 value. Okay, whenever it got the 0 value, it will go to the next state. Okay.
Yes.
Rx underscore in should be 0.
Yes. In frame format, we have taken same way. See here, frame format. Start bit logic 0. For stop bit logic 1.
Okay.
Next, serial in parallel out. So how can we write the logic for serial in parallel out? So module input output range always at the rate of POSIX clock temp 0 run shift. If sample none, temp equal to receiving in, comma 9 down to 1. Else temp equal to temp data out equal to whole temporary value assigning to data out. That means parallel output is assigning to data. And internally, the serial input is shifting to temp. Whatever the receive in, comma temp 9 down to 1 is assigning to the temp the parallel data. And the parallel data is assigning to the D out. Clear this one? Or else if you know any other serial in parallel logic, you can write any logic. Okay. Here I have written in structural, but we don't prefer structural modeling in real time. Okay, clear till here? Any doubts?
No. Yes.
Okay, next parity checker. So before we did parity detection, now parity checker means how can we detect? How can we write the program? Parity checker. So parity
Yes,
checker input, parity in, data in, parity load, parity error, and declare input and outputs. Assign parity error is equal to whenever the parity load is high and parity in not equal to XOR of data in. XOR of data in means suppose there are two ones in the input, output will be 0. Parity in is not equal to 0. What is the parity in? Whenever the parity input is not equal to 0 and parity load is high, then we will get the parity error. That means always the parity input and the XOR operation should be equal. Then we don't get the error, or else we get the error. So data out is equal to getting the parity error. If it is 0, we don't get the error. If it is data in, then we get the if it is 0, we will get the error. Data in means we don't get the error. That's what is this operator? Conditional operator.
This parity load from where we are deriving?
Parity load for enabling here, we are loading at transmitter side. load data, and also here parity load, parity bit error. Parity load is getting from FSM. That means odd parity, even parity, odd
Okay.
parity.
So it is basically we are checking. It means double checking from the frame parity bit and this data whether both are matching.
Parity
Correct.
checker means here whatever the parity load is getting that, and the parity checker value should be same. Suppose parity load you are checking with the odd parity. Odd parity means what? It is 1.
Okay.
Okay.
Means
And
whether
here,
data, it's like whether data is corrupted or not. Correct. Means
so here okay, so here in parity checker you have even number of ones in the input. Before I have written right using the reduction operator, so even number of ones are there in the input. Even number of ones means what? The output will be 0. But here we are checking odd parity. Odd parity means 1. So both are mismatch. Whatever the data input XOR operation we got and parity input, both are not equal. When both are not equal and parity load is high, then we will get the error. But when both are equal, we don't get the error.
Okay.
Okay. So based on the data output we'll be getting. Next. Stop bit checker. How to write the stop bit checker? If stop bit is equal to 1, then we can terminate. Right? That thing we need to write here. Stop bit means what? Last bit. Receiving in of last. So if you see here, module inputs and outputs, assign stop bit error is equal to check stop and 0. Stop bit is 0. Okay. Here stop bit also we are considering as a 0. It totally depends on design. Even if you put 1, you can also put 1 here as a, if you want to detect stop bit as a 1 as error, you can put as a 1, or else you can put as a 0. Next, here we will get the stop bit error. Data out equal to, if stop bit error is high, that means if stop bit error is detected, output will get 0. If error is not detected, output will get data in. Okay. So next, receiver FSM. Same FSM, same as transmitter FSM. Just to go through this, will connect ideal, data, parity, stop, and writing next BS, present state and next state, and the counter logic. And what is the present state and next state, and control signals. Just check this receiver. And now we have designed your receiver and your FSM. Clear till here? Any doubts?
Yeah. Hello.
Yeah.
Hi, ma'am. So no, with respect to SOC level, if we are working with the Synopsys IP for the UART, whether it will come with both the TX and RX, or it will be in the IP side, it will only be TX side. If I just going for that SOC design.
IP TX and RX.
No, it means I have a SOC design. I am planning to purchase a UART IP from Synopsys. Okay.
Okay.
So if I purchase that IP, because but inside that it will be containing both the TX part and RX part. How will be the structure?
They will give both. Overall IP, if you take design you are purchasing.
IP in standalone
Only
IP.
UVC. Okay. Both design and receiver, both you will get.
Okay.
Then receiver side you need to connect with external whatever. Receiver side you can just dump into some FPGA board, or else even your side you can connect actual port.
No, it means if I want to do that configuration, means I have to do because I have not worked with IP side synopsis. If I want to configure, I need to configure both the TX side and RX side simultaneously, or how it will be.
Both you need to design.
Means IP will have both feasibility, both TX part and RX part.
Yes.
Okay. Okay.
Okay, so now we have designed both transmitter and receiver side, and here also receiver block diagram and FSM. Now both transmitter and receiver are completed. What is the major thing left? In top level,
integration.
Baud rate generator.
We have designed the receiver and also designed the uart transmitter. And now we need to design the baud rate generator. For baud rate generator, we don't have the hardware like this block diagram. Directly we can generate the baud rate. We have fixed baud rates. At transmitter side, clock frequency you can take same, and receiver side you can take same and calculate the baud rate. That is one method. Or there are a lot of methods to calculate baud rate. I will show you all. In our code, whatever we used, this is a 2 clock based baud rate. It is somewhat transmitter side and receiver side. Before that, I will explain easy one. So if you see here this example, this is also baud rate generator. Baud rate generator. This is overall uart transmitter and receiver, uart controller. Okay, just put aside, and we will look into the baud rate generator, how it is designed. And if you see here, clocks per bit equal to input frequency by uart frequency, baud rate. Uart frequency is nothing but baud rate. So clocks per bit is nothing but 25 megahertz frequency divided by baud rate is equal to 217. That's what clock per bit. And how can we generate the baud rate further? Divide clock frequency to uart, receiver or transmitter baud rate, with the 16x RX over sampling. Sampling rate will be 16 divisor. Okay. So module baud rate generator parameter clock rate. Clock rate is equal to some 25 megahertz. Huh?
Yes.
Okay, it's okay, 25 megahertz. And baud rate will be here clock, not frequency. It's just given as a 25 000 okay. Baud rate 115200, sampling rate 16 division. Now input clock, input reset, and receiver and transmitter, two baud rates. One is a ORX clock, OTX clock. For transmitter side count and receiver side count, and with taking the values. Transmitter side clock rate divided by 2 into baud rate, and for receiver side also clock rate by 2 into baud rate into RX over sample 60 now. And the TX count with C log, logarithm operation of T, C and T. Whatever the values we are getting here, that C and T value. And here counter value we are considering based on this width, whatever the width we got, that is what actual TX counter and TX RX counter. This is how we calculate the counter here. Okay, but in our code here, count 1 and count 2 directly we have taken 11 down to 0 and 4 down to 0. This is what baud rate. Okay, and here input clock 1 reset, clock in reset, and receiver side 1 clock, transmitter side 1 clock we have taken. And for count between both we have taken directly, but here count also generated using the these expressions. Now receiver side baud rate, how to calculate, how can we write the program?
Hello.
Always, yeah, tell.
So for the ideal scenario, the baud rate of the transmitter and receiver should be equal, correct?
Yes.
No, why that count, that count bit width is different? Means 9th and 10th line.
Here count
Bit
is just it's here count a bit is for just counting the number of clock cycles here. Here
but
we write.
they generated from.
We can take even for this also we can take 11 down to 0. That's not a problem. We can take anyway. Based on count logic also, divisors will be different. The dividers and frequency will be different. Based on that, we'll get the baud rate, right?
Okay.
So here clock receiver and clock transmitter, both clocks are different. Based on that also, the count value will be dependent.
Okay. Yeah, thank you.
Here receiver clock, if reset is high, active low, clock equal to 0 and counter equal to 0, else if receiver count is equal to Rx CNT minus 1, whatever the calculated here, receiver count minus 1. So clock is equal to not clock and counter is equal to 0 and counter equal to counter plus 1. And TX side baud rate, TX counter is equal to TX count minus 1 and clock is equal to not clock, generating the clock for both, and TX count counter equal to 0, counter plus counter equal to counter plus 1. Okay, so both clock frequencies must be same, and these will be generated through the expressions. Based on this TX count, RX count, the main counter logic will be dependent. Okay, so this is how we can write baud rate separately. This is not full code, only for baud rate generation, and this uart transmitter working at 225 megahertz and also 115200 fixed baud rate. Tool I will explain tomorrow. First ask him how to install. TX byte data to send 101010. One 101010. Whenever it detect output transmission is done, input is 01010101, but it is printing here only 101. Okay, 01010110. Whenever it detect, output will be 1. TX ready, input signal. Okay. Here at this point of time, detecting the value and coming to this diagram, this circuit, actual circuit, baud rate generator logic, count 1, clock receiver, receiving clock, transmitting clock. and count equal to count plus 1, and is if count equal to n minus 1, n is declared as 50. So n minus 1 count equal to 0, always at the rate of count. Here count values are fixed. Okay, so same whatever we have written, tx count is equal to tx count minus 1. Whenever you are going through this, check with this example, then only you will understand, because already here defined with the expressions. Tx count means clock rate by 2 into baud rate. So here also same. Okay, and clock receiver is equal to clock, and here also same, count 1 equal to count 1 plus 1, and count 1 equal to 15, then equal to 0. Count 1 equal to 0, clock transmitting equal to 1, count equal to 8, then transmitter clock equal to 0. Transmitter clock equal to transmitter clock. Same. Okay. So this is how we can generate the baud rate, or else you can take the fixed baud rate also without generating like this. Then how you will take the fixed baud rate? In a test bench itself, you can write the frequency directly, frequency and the baud rate. Okay, like this also. Try with examples. You have one more week. This whole week you can try this example. Tomorrow we are going to start with the I2C. Okay, so now we have designed this transmitter, receiver, and also baud rate generator. Now we need to connect these 3 individual blocks in the top level. So how can we connect? What is the top level? Design.sv. Here uart transmitter, uart receiver, baud rate generator, 3. Okay, so 3 are connected in the top level. Input outputs, baud rate generator, DUT, receiver DUT, uart DUT. Okay, now write a simple test bench like this. Test bench you already know how to write, just go through that. Run. Okay, see here, what is the output? Clock tx start. Whenever tx start is high, we'll get the it start the operation, and tx busy is high from here, and data out, data in, input data. What is input data we have given in the test bench? Start is high, input data is a dd. dd means, what is the value of dd? 110 1111 1110 1101 1110. Okay, so 1101 1101, or else you can take decimal, not decimal, hexadecimal. dd, input dd. So here receiving side, 1 by 1 bit it need to transfer, 1 by 1 bit. Okay, dd means how much binary value? 1101 1101. Okay, So 1 by 1 bit transfer, if you see here, this one is transferred, and next 0 transferred, and next 1 transferred, and next 1 transferred, and next 1 transferred, and 0 transferred, and 0 transferred. Like that, 1 by 1 bit is transferring. If you see final value here, 8040A0 D0, like that, final value is getting DD after shifting all the bits. Okay, input is getting parallelly, output is shifting 1 by 1 bit. So at this point of time, we got DD as a output. Clear, everyone? Here, here DD is a input, 1101111101. So first this bit is transferred here. Next 2 bits are transferred to here. Next 3 bits are transferred to here. Next 4 bits are transferred to here. Like that, 1 by 1 bit is transferring. Finally, we got the output DD here. Whenever output DD is got, output is valid. So if you see here, output valid, we got the output valid. Parity error, no parity error. No error, so parity error is 0. No stop error, so 0. Again, data in equal to DD, data out. We got it's a busy state, and also start bit is high. Okay, clear till here? Any doubts? Stop it. Where is stop it? Stop error. Okay, there is no stop error. SIPO out also. See, serial in parallel out output. Like that, parallel in serial out load is high, parallel in serial out shifting. Okay, you can check every signal here sampling. So see here sampling, how the sample is done for every clock. Sample is high, sample is high, sample. That means sampling the data here. Okay, and counter logic in baud rate. However, we took the counter logic. See here, baud rate generator. Wait. So here the baud rate generator can be taken like this for count values, only for count these. For each bit, 8 bits each cycle. 5 down to 0. In each bit, 12 bits it is counting. And TX data out. Okay, like this. So check every signal, you will understand properly. So we got the output here, DD and DD. Like that, try with the more input different cases. And UVM also there. If anyone know UVM, if you want to try, I will share the code. Okay, you can try. Any doubts still here?
Hello.
Yeah.
Ma'am, I was absent last week. So, how to do with this tool? Means, is there in the recorded videos, or can you
Yes.
briefly?
Which one?
That EDA tool which you were showing the waveforms.
Okay. Okay. So, just go to Google or Chrome. Just you search for ediplayground.com. So here this window will be open.
Okay. Do I need to register, login something?
Login. Here you will get the login option. Suppose if I log out, you will get directly login with your Google.
Okay.
You can directly log in with the Google. if you have your office mail ID or student mail ID, you will get the commercial tools also. Here, if you see the tool list, we have AllDeck. AllDeck is free for all. For normal mail ID also, it will be getting. And if you want to use Cadence, Siemens, or Synopsys, all these, you need to use the any official mail ID. So here in EDA, you can write test bench left side and design right side, or interchange also. You can write the design left side and test bench right side. That's not a problem. After writing the design, just select any of the tools. Suppose all deck tool I'm selecting. Suppose here only I'm showing all deck tool select. If you are writing UVM, you can select UVM version here 1.2. If you are not writing UVM, just click none. Okay, and whatever the program is there,
how will be the file hierarchy? If I have multiple files, will be there, correct?
like
so one
this.
by one, I need to add, or I can add the complete folder. How it will be?
Here, suppose design.sv and testbench.sv are default files.
Okay.
Okay, in design.sv, you need to put top level. Suppose here the top level for uart is for top level of uart is this main block, right? I have included all subfiles, uart transmitter, uart receiver, uart baud rate generator. I have included here.
Okay.
So now, whenever you are running the program, these three subfiles and this main module will run. This main module is connected to internal modules. So now it will go to, suppose here TX transmitter means this, it will go to the TX transmitter file when it run. In TX transmitter file, it will connect with the mux, parity, piso, FSM, like that. Okay.
Yeah.
So to test bench, anyway, we write a DUT, right? No need to use any include file here. Just we can use the DUT here. And just click on open waveform. If you want to open the waveform, you know already how to write the $dump file and dump files. To open the waveform, we enable the dumps. So open waveform. If you are writing the coverage for EDA playground, we'll have separate commands for coverage to extract and upload the coverage. So for all deck tool, if you are trying for coverage, let me know. I will share you those commands for EDA. Okay. So whenever you run coverage, run.do file, because we write the commands in Tcl or Perl, right? So just select run.do file only when you write the coverage, or else not required. If you want to open the waveform, just click on open waveform, just click on run here. Run. So after run, the output will be displayed here. The transcript down. Here output or coverage, whatever we write the display statements, everything will be displayed here down. Or else if you want to open the waveform, you can open the waveform like this. Okay, sometimes directly you cannot see these waveforms, then you can go to get signals and select any one and append all or append selected. If you want to particularly just want to select only one signal, then append selected. This is how you can use the EDA. And if you want to save this particular code, here there is a save option. Whatever the save files are there, you can go to the playgrounds and uart playgrounds. In your playgrounds, you will get all whatever you have saved, all will be getting like this.
So if I want to go to UV and TB, do I need to anything specifically mention? Means it means any tool dependency is there. All will be how it will be.
It will, you just need to select here in languages and libraries, just select UVM 1.2. That's it. Okay, tomorrow I will explain QuestaSim tool, how to install. Before that, I will share you some links. I will tell you to download some links. Just download everyone. Tomorrow you can install. I will tell you the installation process. Okay, any doubts still here? Akash, any doubts?
No. Just want to know, like the PPT you're sharing, like it's a drive, right? It will get expired after some days.
No,
Is it?
no. Or else you
Okay.
can download and put in your laptop. You can save
But
it.
I think from the drive, it is allowed, like from the link.
Or else I can share you in the WhatsApp.
Yeah, that PPT, PDF just share. I think that video will get expired, so the link will also get expired. I think that can.
Okay, fine. Hmm? Okay.
Yeah, that's it.
Others, any doubts? Ashish, Aditi, Akhil, Anusha, Ranjit, Roshini, Shubham, and Vinita.
No.
Okay, then.
I had a question. How can we get access to the EDA code that you are writing?
Yes, I will share.
Okay.
I will share all the codes. Okay.
Thank you.
Yeah, thank you.